afternoon all. I am Harshit Derasri. Welcome you all in this online faculty development program on physics. I welcome you all in the fourth day. Before starting our session, let me introduce to our guest. She is a Dr. B.Jotania. She is a professor at Gujarat University in physics department. She will be delivering a lecture on the magnetic ferrites as a microwave absorbers. Handing over to you, ma'am.
So, good afternoon, all of you. And I see, I was reading the name of the participant. Many of you are familiar to me. So, I feel I'm in a home. So, let me talk about the topic which I'm going to deliver today. So, it is on magnetic ferrites as microwave absorber. I chose this particular topic because we learned magnetism as a child also, and it is always a fascinating field for all of us because, and in BSc also we perform so many experiments on magnetism, so the field is appealing to all. And this is the outline of my talk. So actually it is very lengthy lecture, but whatever the part I will cover, I will let you know. So first I will start with the magnetism. So it is part 1, basic of magnetism, and same time I will discuss how many types of magnetic materials are there. In second part I will discuss about the properties of magnetic materials, and third part on ferromagnetic material, especially ferrites, and types of ferrite, characterization and applications of this particular general ferrites. And fourth, we all love to have a nanostructure because they find different properties as well as the it behaves like a new materials, and so many applications of magnetic nanomaterials. So approaches to the nanostructure material including nanomagnetic materials. And last, if you want to prepare the magnetic material, how to prepare and how to test. So it is part of characterization, and there are some standard instrumental technique. They are used to characterize all magnetic as well as the non-magnetic material. And for magnetic material, hysteresis, that is magnetic hysteresis, is very important. And now, since the title is microwave absorber, so ferromagnetic resonance is also one of the most important to check whether the material is used for microwave absorber or not, and it is a hot topic in research also. So yeah, first of all I would like to acknowledge the material which I have taken from various sources, including internet, research papers, books and other publication, including my students' research work. So I would like to acknowledge all of them in the beginning only. And I would like to thank my collaborator and students for their contribution, and some of the work I am presenting they contributed. So first of all I would like to thank my research student Amri, Neha and Preksha, other collaborators from PLU, Professional Lovely University, Dr. Singh, Sher Singh Meena, BRC, he helps us for magnetic measurement, and other foreign collaborators are also there. They also contribute in writing paper and explaining some of the things which are not clear to us, and they are also motivating students. So that is very important aspect. Especially two collaborators I would like to mention. First, Dr. Robert Cipuller, he is from Italy, and second, the Francisco, he is from Brazil and he is working in Army Institute. So he always take our magnetic as well as the network analyzer, means high frequency measurement, and that is our one of the important measurement for checking whether our material used as a microwave absorber or not. And he has a different type of network analyzer, and we are measuring our data in the frequency range between 8 to 12 gigahertz, because most of the radar operate in that range, so it is microwave range and the material is used. So we are checking FMR, and this Francisco is helping us a lot. And last but not the least, Pramod Bhatt, he's also helping us for other measurements too. Yeah, so I would like to just show you some of the students. First Neha, then Dr. Pooler, Pramod Bhatt, Seth Singh and Francisco. These two are the foreign collaborator. Dr. Pooler and Dr. Francisco from Italy and Brazil respectively. Yeah, so now let us start with the basics. So this is the part 1, basics of magnetism. And if you see the below, it is not diamond, but it is basically garnet material, and it is made up of ferrite. So there is always misconception between the crystal and diamond. So diamond is nothing but your carbon, but here the crystal which I have shown, that is not diamond, but it is a ferrite, basically garnet type of ferrite. And if you see the color, that is the color of iron, so it's very appealing. So now let us give you introductions, that is types of magnets. As a child, we always play with magnet, and magnets are available in different shape and size also. So if you see, there are horseshoe magnet, there are ball type magnet, there are simple bar magnet, there are wheel type magnet, there are ring type of magnet, and there are simple magnet. But the color also represents something. So here if you see the red and blue color in right hand side, so it's nothing but you can see north and south pole. And if you compare with the magnetic dipole, so it behaves as a magnetic dipole, and it is equivalent to your polar, like positive and negative in electric field. So bottom I have shown the field, means it is nothing but magnetic needle, and red represents north pole, and other one that represents south pole, and we know the properties. So few you can say pin I have also shown here. So pin also behave as a magnet also, and we know how to prepare or how to convert, you can say simple ferromagnetic material, or you can say material in magnet. So just there are two ways. First, you either pass the current, and other, that is very important, just rub the magnet in one direction. So this new material also behave as a north and south pole. And star magnet is also available, so it's very popular among the children. So as a child, we always look at the this important property, and in high school we also learn few things about the magnetism. So here I have shown various types of the magnet. So first one, if you see number, that is the horseshoe magnet. Second, that is ring magnet. Third, that is cylindrical magnet. Fourth, very popular, north and south is also written, that is known as bar magnet. Fifth is button type of magnet, and sixth, that is square magnet, is also available. And seventh, that is arc, and or it is known as crescent magnet. So there is no any restriction about the shape of the magnet. The magnet can be of any shape, including arc to star and simple your rod also. So magnets, they are available in different shape, size, and you can say the different material also, including ferrite. And this is very well known to us. So magnetic needle compass, it shows the direction north and south, and this is very useful for navigation purpose. And this is one of the simplest use of the magnet. It shows the direction north and south pole. Now, as a physicist, we always have a question, or as a, you can say, curious people, or we always have a questions, why do some materials respond to magnetic field while other do not? So answer is very simple. So magnetic materials have a property known as magnetization, known as capital M. It is vector quantity as quantified in the relative permeability constant, that is mu r. So all magnetic materials, they have a magnetization, and it is defined in terms of magnetic permeability constant, that is mu r, and this is very well known. So now let us learn about the permanent magnet. So again, if there is a permanent magnet, they have a magnetic dipole moment such as current loop. So here I have shown the north pole and south pole, and direction of the magnetization is south to north, and it is believed that the magnetic line, field line that comes out from north pole and reach to south pole, and it is, you can say, continuous lines. So this is magnetization or magnetic field lines. And we also know that if we place two magnets nearby, then like poles, they repel. So in a non-uniform external magnetic field, permanent magnets experience a torque, and that is also calculated. And you know, the unlike poles, they always attract. So north and south pole attract, north and north, or south and south, they repel to each other. So this is very important properties of the magnets. Very simple but very important. And yeah, so the net force in the direction of the stronger magnetic field, so that also we know. And yeah, so now let us see the history, and we always like to know about the magnetism. So this word magnetism comes from the region called Magnesia, and where you can say this material known as magnetite was found, and the common name for that is lodestone. So magnetism comes from the region called Magnesia, where lodestone, or you can say magnetite, was found first. And here in circle I have shown the place where the magnetic material or lodestone was found first, and this place is located in Greece, and it is marked as green, and this is known as the Magnesia, that is the part of Greece. Here you can see first magnetic material was found, and this is the person who talked about the magnet. So he is Englishman known as William Gilbert. In 1600 BC published the magazine that is known as The Magnet, where he described magnetism as the soul of the earth. And we know now, because soul means earth also behave as a magnet. So he was the first person to say about the earth magnetism, and he mentioned that the earth also behave as a magnet, and it is a soul of the earth magnetism. And he also mentioned that if you take the spherical magnets, then a perfectly spherical magnet spins without stopping, because earth is a perfect sphere. It is it's a magnet and it spins without stopping if it is perfectly sphere, but we know it is not perfectly sphere, but he assumed for simplicity. So it has also poles, and north pole always represented by showing arrow, and south you can say just the back side of the arrow, and this is the red line shows that it is a spinning. So you can say north and south pole, and your this magnet is rotating continuously without stopping, means continuous. So now let us talk about the description of magnetic material properties. So for accurate quantitative prediction, generally quantum theory is required, but for qualitative description, you can say orbital mechanics model is sufficient. So which type of whether you would like to say about the quantitative or qualitative, according to that you have to choose the different theory, quantum theory and orbital mechanics model. So here in orbital mechanics model, it has a orbital moment, and proton, it has a positive charge, neutron. So atom has electrons that orbit around its nucleus, making a miniature current loop that results in an orbital magnetic moment. So next one, that is the electron spin around its own like sun and earth relation, and to produce the significant spin magnetic moment. So you can say we have a two magnetic moment, orbital as well as the spin magnetic moment in this model. And in orbital mechanics model, the relative contribution of magnetic moments of each atom and the molecule makeup of material classified into different category. For example, diamagnetic material or diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic, and last one, that is the superparamagnetic material. Any atom with a magnetic moment in the presence of applied magnetic field will experience a torque that tend to align it. So although you can say magnetic dipole, they will align in the direction of the external magnetic field. So now let us talk about the domain. So all of you must be teaching about the domain in ferromagnetic material and domain wall also, motion of the domain also. So let us see what is domain. So it is nothing but a region within a ferromagnetic, or you can say ferrimagnetic material, having a large dipole moment due to the collection of associated atom with uncompensated spin moment, and known as, you can say, region, you can say, in which it is a small region, very small in size, but if you look in that particular region, the all, you can say, dipole, they are aligned to each other, and if you move from one to another domain, the direction will change, and in between there is a sharp region that is known as domain wall. Then second thing is shape, size and direction of the magnetic moment varies between neighboring region within a crude sample that cancel the effect overall. So at room temperature, they don't behave as a magnet. So how do we understand ferromagnetism? So if we consider the concept of domain, then it is easy to understand. So small region that have aligned dipole moments are called domains. In non-magnetized iron, the domains are randomly oriented as shown here. So if you see left hand side first, the direction of the spin, or it is nothing but, you can say, net magnetic moment is some other direction. If you take another region or another domain, you can say direction is different. So this is net magnetic moment, and it is vector. So if you take the addition, the net magnetic moment is 0. So here domains are shown. It is a small region, and net magnetic, or you can say net magnetization is shown in particular domain, and various domains are shown, and these domains, they are part of your ferro or you can say ferromagnetic material. Fine. So in a permanent magnet, the domain tend to be aligned in a particular direction. It is direction of the applied field. And if you apply the external magnetic field, what happens? This magnetic moment will try to align, depend upon the force of the applied field, and after if it is sufficient, all you can say domain, they are aligned to each other, or you can say magnetic moments in domain, they are aligned to each other and shows the net magnetic moment, and that is the characteristic of the permanent magnet. Fine. Alignment of the magnetic domain so may be achieved by applied external magnetic field, and upon removal of an external magnetic field, domains do not all return to their original state, and thus it exhibits a magnetic history that is known as hysteresis or magnetic hysteresis, and interesting and particular effect unique to all ferromagnetic as well as the ferromagnetic materials. So ferromagnetic as well as the ferromagnetic material, they shows the particular magnetic history known as magnetic hysteresis. Fine. Here I have shown the example of different type of magnetic materials, and these materials it very well known to us. For example, diamagnetic. So if you see right hand side, the elements and compound is listed: bismuth, hydrogen, helium, sodium chloride, gold, copper, silicon, germanium. They are part of diamagnetic materials. And paramagnetic materials, potassium, oxygen. Ferromagnetic, you can see used for permanent magnet. For example, iron, cobalt and nickel. Antiferromagnetic material is also there, majority oxide and sulfide chloride including, for example, MnO, nickel oxide, FeS, cobalt chloride, etc. Ferrimagnetic, all ferrites including iron oxide magnetite, nickel ferrite, it is spinel ferrite and hexaferrite. So you will also learn about types of the ferrite. And super paramagnetic materials, ferrimagnetic particles in a non-ferromagnetic matrix. So that is so it has a very particular or typical hysteresis. So if you take the hysteresis loop of all this material, you will come to know which material. So that is one of the, you can say, identification. If you take the hysteresis, looking to shape and size of that, you will say this material is ferroferry or super paramagnetic also. Fine. Second part, very important, properties of magnetic materials. They shows various different properties, and one of the property I have discussed, that is magnetic hysteresis loop. Yeah. So now the question is how magnetic materials look like. So they are available in the powder form. They are also available in liquid form also. So first, dry powder, and this particular shown for nano. So it size vary 10 to 100, and example is gamma Fe2O3, Fe3O4, cobalt ferrite, manganese zinc ferrite. So my point is magnetic material, they are available in powder form also. And they are also coating with some other material. For example, here magnetic nanoparticle, they are coated with the non-magnetic material, and here it is specially used silica. And right hand side you can say it is image of TEM or transmission electron microscope image, TEM image, very useful to check the nano, especially nanomaterials. Here it is of 10 nanometer. So second, I mentioned that it is also available in fluid also. So magnetic liquids consist of magnetic nanoparticle with a narrow particle size distribution, can be around 10 nanometer, covered with thin film, or you can see inorganic or organic dispersant, which protect them against agglomeration. So if you want separate particle, so coat this particle with some other materials, maybe carrier liquid like water, oil, or you can say hydrocarbon, etc. So magnetic particle can be also coated with the various liquid like water, you can say oil, or you can say other hydrocarbon, etc. So here I have shown the picture of magnetic nanoparticle, or you can say fluid in nanoparticle. So backside you can say magnet is kept, so this shows the spike. So magnetic liquid based on organic carrier liquid, and here also you can say magnetic liquid based on water as a carrier. So carrier can be anything I mentioned. It can be oil, it can be water, and it can be other hydrocarbon, depend upon for which purpose you are preparing the magnetic liquids known as magnetic ferrofluid. Yeah, so this is coated iron oxide nanoparticle, and it looks very beautiful, and it shows the spike. And if you change the magnetic field, the spike also vary. So some of the people, they also prepare or do some creativity using change in the magnetic field, and you can say they play with the magnetic fluid also. And this material is very useful for sealing purpose. Yeah. So this you can say liquid, they are used in industry, medicine, as well as in biotechnology also. So magnetic liquid present a new class of the magnetic materials with a wide range of applications. For example, in industry, they are using for sealing purpose, dumping purpose, cooling, bearing, sensor and loudspeaker also. In medicine, very important aspect, diagnosis of therapeutic applications such as MRI, targeting drug delivery in cancer therapy and hyperthermia, etc. And in biotechnology, they are used for cell separation and cell sorting, etc. So now let us focus on ferromagnetic material because our group is working on ferromagnetic material, and they have also found very large number of applications, not in industry or you can say in scientific or technology, but you can say day-to-day life. And one of the application I mentioned that they show very beautiful they means reflectivity, so they use as a jewelry also. Fine, so just let me say something quick because all of we are not too much interested in too much detail. So ferrites are nothing but ferromagnetic materials and have outstanding magnetic dielectric property and many other unique characteristics also. For this reason, they have attracted huge academic as well as industrial research, and broadly they are classified into 4 different groups. For example, spinel, garnet, ortho, and hexa. So all the ferrites, they are broadly classified in 4 main groups. And this is simple spinel ferrite, and it has a cubic structure, and it has application basically in biomedical application and magnetic sensor and magnetic recording also. And this is the structure of cobalt ferrite, COFE204 spinel, and 2 different sites it has shown here, A and B site, and the formula is AB204. Yeah, so I said the spinel, and if you go for jewelry shop, they keep such type of spinel, and they are nothing but you can say magnetic material. Due to its excellent hardness and high clarity, spinel is an excellent gemstone for all types of the jewelry. And if you see, they have a different color because the content is also different. So here I have shown 3. So many famous large rubies in the crown jewels around the world are actually spinel. They are not, you can say, diamond, but they are spinels. This is the another crystal structure for you can say garnet, and a group of isomorphic minerals crystallize in cubic system. They are used for gems, and these are the materials. I said why they look different because the chemical composition is different, so their color are different. Some of them are, you can say, reddish, or you can say maroon, or you can say black or blue. So it depends upon the material or you can say chemical composition of that. And crystal structure, if you see, that is the complex, and this is the crystal structure of the garnet, which I have shown just now. This is nothing but again garnet is gems, belong to the semi-precious stone category. And look, there are different color from green to maroon, even light black. Also, they are transparent, and they are, you can say, semi-precious stone category. And again, these are the garnet, or you can say garnet gemstone. And it is believed that the garnet is known as the stone for successful business. So if you want to do good business, you keep such type of, it is believed. I don't know how much it is successful, but the garnet is known as the stone for successful business. And see the color, the colors are very different. It look very attractive, including purple, red, brown, and you can see saffron type of gemstone is also available. So basically they are garnets. Yeah. So I mentioned they are used in jewelry also. So these are the garnets, and they are used in, you can say, bracelet, or you can say earrings and ring also. So they are very famous in preparing, you can say, jewelry, but they are not, you can say, diamond. They are just, you can say, precious stone, or you can say semi-precious stone, like garnet or spinel. Fine. And this is orthoferrite. This is another type of ferrite, and it has a orthorhombic crystal structure, and they are mostly weakly ferromagnetic, and the formula is RFO3, and R is the rare earth garnets. Fine. So third is, you can say, hexaferrite, and this is very well known structure known as magnetoplumbite structure. And this material has a strong uniaxial magnetic direction, and that's why majority of hexaferrite they are used, especially M type of hexaferrite used as a permanent magnet. And I think more than 70% magnets are made from this. So you can say this, or you can say combination of composite also. So it covers, you can say, majority of market for the permanent magnet. Yeah. So what are the applications of hexaferrite? So compared to other, they have a more technological applications. For example, electromagnetic wave absorber. They are used in microwave devices. They are used in microwave components like isolators, phase shifter, circulators. Sorry. They are also used in computer data storage. They are magnetic recording applications and microwave monolithic integrated circuits. So hexaferrite, they have a wide range of technological applications. So it has some more importance compared to other magnetic materials, or you can say ferrite materials. So I have shown some of the components where you can say ferrites are used. So this is isolator, and right hand side this is known as circulators. Both are used as microwave components. So for EMI separation, they are also used. So these are the ferrite cores. They have a different shape and size also. So ferrites are also used as a transformer. So these are the core and transformers also, and they are also used as a core. So this is one of the core, and right hand side, left hand side transformer is there. This is also used in planar inductor. So these are the various technical components where you can say ferrites are very useful, especially hexaferrites. So more applications. So ferrites are used in high density magnetic and magneto-optical recording media, including home appliances, electronic products, communication equipments, and data processing device. They are also used in MRI, magnetic resonance imaging. And again, hexaferrites, I said, divided into 6 different types. So in that, you can say M, that is the magnetoplumite, and second one, that is Z type of hexaferrites, especially cobalt-based Z-type hexaferrite. So in that, complex permeability measurements, that is ferromagnetic resonance property is very important for this material, and it will decide whether this material is used as a microwave absorber or not. Moreover, this material is also very useful for terrestrial digital multimedia broadcasting known as DMB antenna for mobile phone applications. And we cannot think our world without mobile phone now. So this is the material used in antenna for mobile phone application. Second application is high frequency electronic devices such as multi-layer chip inductor. So ferrite are also used, especially Z type of ferrite, cobalt based Z type ferrite is used in that particular application. And here few more application I have shown. An integrated coplanar waveguide tunable phase shifter. So if you want to change phase, then you use such type of component. So the outcome outside the frequency will change compared to in phase. So first, that is the moldable polymer ferrite composite known as MPSC. And here if you see right hand slide, black S-shape material, that is the ferrite. And if you take second terminal, your phase is shifted, and right hand side some of the properties shown, that is measured bulk property of fabricated MPFC, and bottom you can say the construction is shown, and see the hysteresis loop, very narrow hysteresis loop, and that is one of the characteristic of Z type hexaferrite. And right hand side again if you see, there is a applied magnetic field versus absorption power, and peak is also shown in that. Fine. So next is approaches to nanostructure material. So that I am going to discuss. So next part, approaches to nanostructure material. So I covered this particular because the material behaves very differently compared to bulk material. So APJ Kalam once said, nanotechnology is knocking at our door. It is the field of the future that will replace microelectronics and many fields, with tremendous applications potential in the areas of medicine, electronics, as well as material science. And this is from eminent scientist Professor C.N.R. Rao. India cannot afford to miss the nanotechnology revolution and must make investment in the area very carefully. And third sentence is mentioned by Larry Purcell. India can lead the world in nanotechnology in the next 10 years. India has got the brain power for this, what with its large pool of alumni from the leading university, IITs and IIMs also. So now let us focus on lowering of the size. So if you see the left hand side, it is our PC. PC is replaced by, you can say, laptop and then palm top, and now you know we have reach to the nano age. So stepping toward the miniaturization, the drive to minimize electronic components contribute to the onset of the nano age. So size calibration, and this is very famous chart. So vary from, you can say, 0.1 to 10,000 nanometers. So 0.1, that is atoms and ion comes. Then proteins come between 1 to 10 nanometer. DNA is nearly less than to slightly greater than 10 nanometers. And magnetic nanoparticle, that comes in around 100 and more than 100, or you can say around 200. Then you can say 500, 4 to 500 nanometers, bacteria and cell nucleus. So limit of optical resolution. So up to here you can say optical resolution can be carried out. Then you can say 10,000, 1,000 to 10,000 also. So bacteria reach, you can say slightly greater than 10,000, and you can say 900 to 1,000 cell nucleus comes. So this is, you can say, size calibration for nano. So how size matters? Size dependent property. All the various property, they also depend upon the size. For example, magnetic properties, optical properties, melting points of the material, surface reactivity also depend upon the size. Bulk materials of nanoparticle exhibit totally new properties. So that's why size matters, because it changes properties, various property including magnetic, optic, melting, surface reactivity, etc. So what do you mean by nanometer? It is 1/1000th of the meter, and here the size of various elements and you can see DNA and cell are shown. For example, hydrogen atom, the size is only 0.1 nanometer. Diameter of DNA around 2 nanometer. Poliovirus, it is 40 nanometer. Red blood cell, 10,000 nanometer, and human hair width is around 80,000 nanometer. So nanometer is extremely small unit of length, and nanotechnology typically deals with the particle and structure slightly greater than 1 nanometer and less than 100 nanometer. So the size between 1 to 100, they are come in nano. Here I have shown the structure of DNA. So it is 10 nanometers. At the center of the cell, it is slightly coiled molecules called DNA. It contains the genetic material, and we all have studied about DNA in our high school, or you can say 11th standard. Fine. This is the poliovirus structure, and it is size is around 40 nanometer. Then human red blood cell, the size is around 10,000 nanometer. The cells developed in the bone marrow. Approximately a quarter of the cells in the human body are red blood cells. Human hair, I have mentioned, it is around, you can say 80,000 nanometer. So size is very high, and we can feel if we touch. So for this much size, we can feel, other we may not feel. Fine. So now let us talk about the magnetic nanoparticle. So magnetic particle of nano size are attracting growing fundamental as well as technological interest because of their unique magnetic property, which are dominated by a special magnetism called superparamagnetism. And all, you can say, magnetic nanoparticle shows the property of superparamagnetism, and it has a very extremely narrow magnetic hysteresis loop. So that is one of the characteristic of magnetic nanoparticle. The unique property of nanoparticle and size depend upon large number of applications. This material such as pigment, then magnetic agents, lubricant additive, etc., as well as the microwave and shield technology, including production of the ferrofluids. Fine. So again, nanomaterials or nanomagnetic materials, they are divided into two parts. So first one, system with nanomagnetic dimension, known as cluster or nanoparticles. And second, the system with macroscopic dimension but made up of crystallites with nanomagnetic dimension. For example, nanostructure or nanopattern materials. They differ from bulk material by intrinsic property of isolated cluster, coercivity, remnant magnetization depend on the structure, and specific property resulting from coupling between constitutive and nanocrystallites. Fine. So now let me focus on this fifth part, that is the preparation and characterization of the ferrite material. Any material, the characterization is very important because it shows the various property and decide the quality of the material also. So you can say the characterization is very important, and you can say material, they are especially magnetic material, they are prepared using various experimental technique, and for that you can say various techniques are used, including recent technique. For example, ferrites, or you can say magnetic material, can be prepared using ceramic method, very old method, and there are some limitation because high temperature sintering is required, and most important, the final product is always particle. They are very coarse and some impurities always occur because of long crushing hours as well as the high heating temperature. So that was not adopted, but in industry we were using long bed. Then wet chemical, it is aqueous base, so compared to previous, this is better. And particle homogeneity, if you want to get, you can use wet chemical method, because the reaction occur in a wet medium like water, or you can say some ethanol or other medium. Then there is also again limitation because there is some byproduct is also there, lot of wastage of water. Then new method come, that is known as autocombustion method. It is very popular because during 5-6 hours you will get the final product. Then to increase the reaction rate, citrate gel occurs. Then micelle, very popular for nanoparticles, but again limitation. The final product is very less in quantity. And sol gel is also very much useful, hydrothermal, and recently very popular, that is green synthesis method, and I will also show you some of the slide about the green synthesis and what are the advantages of green synthesis. It is very non-toxic method. And the structural as well as magnetic, also dielectric property of hexaferrite depend upon not only hexaferrite but other ferrites and magnetic materials depend on many factors like method of preparation, sintering temperature, type and amount of substitution, sintering time, etc. So which type of material you want to prepare, according to that you choose the route as well as depend upon, you can say, reaction rate, time, heating and cooling temperature. All the parameter depend, means it will decide the structural as well as the magnetic property, or these parameters will affect both magnetic, dielectric as well as the structural properties. Fine. So you require very simple equipment to prepare magnetic material. For example, left hand side, furnace, very popular, and minimum you can say like our cooking gas, we need a furnace, and for you can say pressing the pellet and heating purpose, hydraulic press is also used. Fine. So I was talking about the green synthesis. This concept is extremely new and known as green chemistry. A new kind of chemistry, also known as the chemistry of nature. Why it is so popular? It is safer, very, very important aspect. Smarter compared to other route, more efficient, conserve energy, prevent pollutions, and design for reuse and recycle. So you can use reuse same thing and recycle the material. So that's why green chemistry is very popular. And what is green synthesis? It is also known as sustainable chemistry. So definition of sustainability. So sustainable development is the development which meet the need of the present without compromising the ability of future generation to meet their own needs. So means preserve the thing, and this is very important statement by G.H. Bentel from Oxford University Press, Oxford in 1987. So, let me talk more about the green synthesis. It is based on simple aqueous process using plants, leaf, flower, root extract, and they works as a precipitation in salt gel. So extract from plants acts both reducing as well as the capping agent in synthesis. Reaction at room temperature, very important. No need for, you can say, high temperature, or you can say heating the material. So that is one of the important aspect. At room temperature, reaction is possible. That's why it is cheap, it is eco-friendly, it is non-toxic, because we are using the plants around us, and non-air sensitive precursor, and most important final product that is relatively large yield, around 10 to 20 gram obtained within a few hours. So that's why this green synthesis is very popular. And you can say hexaferrite also can be synthesized using green synthesis. So some of the students, they are working on neem, aloe vera, eucalyptus plants extract. Students are also using ginger root, because ginger is very popular in our culture. Then fruits also, like tomato and star fruit. And some of the researchers, they use spices like cloves and cinnamon to prepare the hexaferrite materials. Okay, so next is why the solution combustion. So again, it is very simple, low cost. So after green synthesis, this combustion is very popular, and when the green synthesis is not so popular, that time the material where preparation was carried out using the combustion method. So because it is very simple, low cost, not required very sophisticated instrument, energy saving, because within 4-5 hours you prepare the material. This method produces homogeneous, porous, with high surface area material, and the entire preparation process complete within a few minutes. You can say this is only combustion, not you can say preparation. Less than 5 minutes, combustion is over. And sometimes different fuels are used. I mentioned citric acid, nitrate also, and sometimes urea also used to increase the reaction rate. They works as a you can say catalyst. And here means very simple method shown, that is known as auto combustion method using ammonia and metal nitrate. So this work was given to one student, strontium zinc, iron ferrites, and citric acid was used as a fuel. and water solution, and ammonia was added. So you know acid plus base is equal to salt plus water. She has shown different, and this is the final product, strontium zinc Fe12O19. So this is M type of hexaferrite prepared. And this is the flow chart how the material was prepared. So all the nitrates were taken, strontium nitrate, iron nitrate and citric acid. So if you mix, it becomes the citrate nitrate solution, and ammonia was added 30% weight per volume. pH was adjusted around 7. Then thermal dehydration to form the gel, and auto ignition starts. So various stage here I shown right hand side, that is part of auto ignition. So first is liquid mixer, then heating is done. So it is dry heating, no water was added in this. So backside you can say hot plate is there, then self ignition starts. So then you can say the material is coming out, and you can say right inside bottom, if you see, it is the final material, and that is nothing but this SRM hexaferrite, M type of hexaferrites. And same thing, just repetition, solution, then right hand side gel, auto ignition and magnetic nanomaterials. And this material was prepared by my student Nital. Now she's working in MG Science College. And same thing, if you want to prepare the nanoparticle, this is very popular technique known as microemulsion, but only limitation is a lot of byproduct is there, so wastage of material, and final product is very small. But if you want uniform nanoparticle, this method is extremely important because it gives very small, you can say nano-size particle, uniform particle. And when you go for any application, uniformity of particles are very important. And second thing, the shape is also important for medical and other application. And so microemulsion are nothing but thermodynamically stable, optically transparent, isotropic, dispersion of aqueous and hydrocarbon liquid stabilized in an interfacial film of surfactant molecules. Microemulsions are monodisperse spherical droplets, and as mentioned that the nano related with 1 to 100. So diameter is here less than 100 nanometer of water in oil or oil in water, depending upon the nature of the surfactant. So that's why it is known as microemulsion as well as the reverse microemulsion, depend upon whether water is in oil or you can say oil is in water. Fine. So here the shown the difference between macro and microemulsion. So macroemulsion, that is kinetically stable, but the microemulsion is also thermodynamically stable. And microemulsion droplet size is between 10 to 100, but it is transparent. And macroemulsion, you can say 1 to 100 micrometer, and it is opaque. In microemulsion, the final product has a high surface area, whereas the macroemulsion, they have a low surface area. Fine, and here it is shown how the preparation of nanoparticle using microemulsion. So two microemulsion prepared, microemulsion 1 and 2. One is metal salt like FeCl3, FeCl2 or copper chloride, and microemulsion 2, that is nothing but base like NH4OH or N2H4 or NaBH4, etc. So if you see this aqueous phase in a oil phase, so mix microemulsion 1 and 2. So collision will be prepared, and final you can say precipitation in, you can say small droplet of the water. So it is metal, or you can say metal oxide, including hexaferrite prepared using this method. And micelle in this system can be described as nanoreactors providing a suitable environment for controlling nucleation and growth. In addition, at the latest stage of the growth, steric stabilization provided by the surface layer prevent the nanoparticle for aggregating. So it's very important. They should not collide to each other, otherwise it will make the large droplet. So the reaction in water is very important, or you can say oil, depend upon the you are using micelle or river micelle technique. Fine. So where these magnetic particles are used, so I mentioned it, they are also used in biomedical applications. For example, magnetic hyperthermia. Similarly, magnetic biodetections, these magnetic particles are used. Targeted drug delivery, then magnetic separation, they are used. Magnetic resonance imaging, MRI is very important tool for medicine or medical field. Then magnetic particle imaging, MPI, and if you see the particle size vary, so depend upon the shape and size of the particle, applications are there. So in figure you see 120 nanometer scale, 200 nanometer scale, and so on. So depend upon the type and shape, the applications are decided, and these are the general applications of magnetic particle in biomedical applications. And here they are also used in cancer as contrast agent. So if you see here the purple and non-purple cell, so this purple cell, they are nothing but cancerous cell. So in patient, or you can say how much percentage of the cancerous cells are available in a particular area, that can be decided, and so according to that magnetic treatment, medical treatment can be given. So that's why this magnetic nanoparticle, they are used as contrast agent also. So only you can say the particle will deposit it on cancerous cell, they will not deposit it on other cell. Fine. So I was mentioning the characterization technique. So this is very important tool. You have prepared the material, but how to test? So for that you can say standard characterization techniques are available for different material. Fine. So instrument techniques are used, for example, X-ray diffraction, then to decide the phase purity as well as the lattice parameter of prepared material, especially ferrites. Then FTIR is also very popular. Then TGA, DT and DSC also used. Same, that is to check the surface morphology of the material, and if it is nano, then transmission electron microscopy is very important. For checking the magnetic materials, VSM and MOSBA techniques are used. So you can say structural, magnetic and dielectric property. For different property, different instruments are used. For example, structural, we are using X-ray and FTIR. Thermal property, we are using TGA, DT and DSC. For checking the surface morphology, SEM and TEM is used. And for checking the magnetic property or measuring the magnetic property, VSM and MOSBAR are used. And for dielectric material, depend upon the frequency, LCR meter is used for 2 megahertz frequency. And suppose you want to test the microwave absorption, you require the network analyzer from 8 to 12 gigahertz frequency, and it's very costly instrument. All the instruments are very costly, and you have to collaborate, or you have to go other place for the testing. Okay, so here I have shown the just X-ray diffractometer, how it looks like, and how the right hand side, the chart that is known as X-ray diffractogram, and here this is M-type material, but here it is not barium or strontium, but it is lanthanum base, And I was mentioning to check the phase purity and crystallite size also can be checked. Not only that, but you can decide the lattice parameter, for example, A, B, and C, and cell volume, and so on. So if you see here the red mark dot in some of the chart, so it shows it is nothing but length LFeO3 is formed. Then if you see the square, it shows that the Fe2O3 is there. So these samples are not, you can say, pure. It has a 2 secondary phase of Fe2O3 and LFeO3. So if you have an impure phase or secondary phase, then this material cannot be used for application. So you refine your method to get the pure phase. So this way we can test the structural property and phase purity of the material. So in this material, you can say it is not pure ferrites or M type of hexaferrite, but it has 2 different phase or secondary phase Fe2O3 and LFeO3. So if you want to remove this 2 phase, you have to modify the preparation technique. And here, if you see, the bottom is the sample was heated 24 hours at 1300 degrees centigrade, and again they have heated 24 hours at 13,080 degrees centigrade. Then what they have done, they have increased again 117 hours same temperature. So here they are trying to increase the you can say sintering hours, keeping the temperature constant. So people also change the temperature. For example, in bottom the temperature was 1300, then they just increase around 100, so it is just less than 100, 1380. Time they have kept constant, but temperature is increased. And third, they have kept temperature constant, but the number of hours increased. So if you see first and second and third, what is different? In third case, you can say there is no, you can say alpha Fe2O3, actually it is alpha Fe2O3, it is non-magnetic phase, and even there is no LFeO3. So they have just refined and found the phase purity of the sample just by increasing temperature as well as the number of hours, that is the sintering time. So it's very important. So the FTIR means very crude measurement. So it gives the stretching and vibrations, and in ferrite we decide whether it is, you can say, very crude. We just check 2 bands are formed, you can say the ferrites are formed. So, and different material, they require different characterization, and they give basically stretching vibrations of the chemical bond. Fine. So TGA will decide whether endothermic reactions occur or exothermic reactions occurs. So left hand side, the thermogravimetric analyzer is there, very small in size. You can keep on our table. So it decide heat flow and melting point also decide using, and how much loss is there of final product, that is known as weight loss. So if you design any device, but after heating, if the device shrunk, then material is not very stable. So for temperatures, stability is very important, and we have to check using the TG and DTA curve. Fine. And I mentioned to check the surface morphology, whether the formed particles are uniform, agglomerated, or they are not showing proper shapes, and how much void is there, that can be tested using the scanning electron microscope. So left hand side the instrument is shown, and on the screen of monitor you can see the image, and right hand side you see the boundary also. So age is very clear, but the shapes are not uniform, and you can say the formed particles, or not particle, but here you can say grains. Grains are non-uniform and not agglomerated, but they have a different shape and size also, so that you can and if you have a image software, you can also see the distribution of the particle in this particular surface area. So various softwares are also used to test the surface morphology and to check the grain size variation. Fine. So I mentioned for nano, this TEM is used, and left hand side transmission electron microscope is shown. Photo of that. And right hand side, the actual photographs or image, transmission electron microscope image is shown for. And if you see the scale, it is 100 nanometer. So you can see all particles, they are exactly maybe larger, few are larger and few are lower than 100 nanometers. So they are not uniform, but you can see non-uniform particles form, and they are distributed over the surface. And I mentioned for magnetic materials, you require this magnetic sample magnetometer, and it gives the hysteresis loop. So if you see the right hand side, there are three different hysteresis loops shown. A is the autocombustion powder without heating. That is the A lowest, so saturation magnetization is lower. So if you heat the sample 1200 degree in air, the B, that is the saturation is increased. And third one, again, combustion is heated is 60 degree in air, argon, using argon, that is the gas. So saturation magnetization is increased, and high magnetization, it's very important, or it is good for magnetic materials. So again, it depends upon the distribution of the ion in different sites. So saturation magnetization is nothing but net magnetization of different site. So nowadays there is a need for high power magnets. So nanocrystalline yttrium, samarium, cobalt grains possesses unusually large surface compared to traditional magnetic materials. So that's why they are used for high power magnets. It allows for much higher magnetization value. Possibility of quitter submarines, ultra-sensitive analyzing devices, magnetic resonance imaging, MRI, or automobile, alternated to a name a few. Okay, so thank you very much for your kind attention, and if you have any questions, query, welcome.
Ma'am, there is a question from Dr. Devang Shah. Is this magnetic measurement facility available at Gujarat University?
No, we don't department, but okay, sorry, we don't have that facility in our department, but nearby in NCL, National Chemical Laboratory, Pune, we can go for this measurement either by payment, or if you send them request, sometime they also test freely, depend upon the how much important your material is.
Ma'am, we have one more question from Prashant Kumar Vachani sir. Is there a report about the synthesis of magnetic oxide using green method at room temperature?
Sorry. Okay, Prashant bhai, your question is there any report available for green synthesis at room temperature? Yeah, there are some literature, but it depends upon the which type of material you want to prepare. With simple magnetic oxides, it's possible, but if you go for, but again it depends upon the room temperature. Again, if you go for a country like USA where temperature is too low, so their room temperature is different. But if you do same thing in here in India, so our room temperature is around 40 degree. So you just go through the literature, which material you would want to prepare, and according to that, but there is no review because this green synthesis is very recent concept, so there is no review. But for other magnetic material, many good reviews are available. For example, for hexaferrites, we have a very good report from or you can review from Dr. Pooler, so that you can read, and he also started some work on green synthesis. So you just look at the literature and find out the which type of material you would like to prepare, and room temperature vary depend upon the country, so that you should keep in mind.
Thank you very much, Dr. R.B. Chotania ma'am, for your valuable time.